Hi, welcome to Chapter 12. And those of you from Shady Spring High School, please have Mr. Gunther send my check. So this is how this works. This is how this works. You've got the pressure of the gas pushing in one direction. And then you have air pressure pushing in the empty tube. And then you have mercury that normally would be level, but one side is going to push more than the other side, so it's not going to be level. So just by looking at this, which one's bigger, the gas or the air pressure? Gas. The gas, because it pushed it that way. And then this is where it's either adding or subtracting. It's bigger by 60 millimeters of mercury, because that's that one conversion. And really, if you can do the manometer problem, then you can do the pressure conversion problems, because you have to. Because you can't add atmospheres to kilopascals or torrs to whatever. You can't do that. So you have to make sure everything is in the same unit. And all these are either adding or subtracting. That's all there is to do. So I said that the air pressure was 98 kilopascals. And that's smaller. The gas pressure is bigger than that. So it's going to be adding or subtracting. If I want to get the gas pressure, what am I going to do? Add or subtract?
Subtract. Add.
Going to add.
50%
Yeah, because those, yeah. Because gas pressure is bigger. You just told me the gas pressure is bigger. Bigger than what? It's bigger than the air pressure. So bigger than means you have to add. So you're going to take the 98 kilopascals and add it to the 60 millimeters. You just have to remember that that's actual mercury, because that's what that Torricelli guy did when he was wandering around Italy. He had the open pan of mercury and it went up inside the tube. And he measured it, and that's where that comes from. So you're going to add. The problem is you can't add millimeters of mercury and kilopascals. It's like adding a meter and an inch. You can't do it. So you have to have it in the same unit. And then, because I specifically asked, what is the contained gas pressure in kilopascals, you might as well change that to kilopascals and add it to that. Then you'll be done. So that's what I'm going to do. I'm going to take the 60 millimeters of mercury and I'm going to stick that over 1. I'm looking for kilopascals, so that goes in the top. Millimeters of mercury goes in the bottom. And then on your equation sheet, you are allowed to write 1 atmosphere. And this is the pressure. This is air pressure at sea level. And that's where we get this conversion from. 1 atmosphere is equal to 760 torr, is equal to 101.3 kilopascals. And is there something else? 760 millimeters of mercury. Those are really the only ones that we're going to use. There are other ones, and you can put them on there too. 14.7 pounds per square inch. I don't think I give you anything English on the test though. Pretty sure. So in front of the kilopascal, I put the 101.3. In front of the millimeters of mercury, I put the 760. Millimeters of mercury will cancel out. I take 60 times 101.3, divide it by 760. I get 7.997, so I'm just going to call that 8. This is 8 kilopascals. The gas pressure is bigger than the air pressure by 8 kilopascals. So what is it, 106?
Yep.
Yeah, and it'd probably be good on the test if you actually showed that you added, just so that I know what you did in case you do something crazy like not add them correctly, which I do all the time. Just do that. Okay?
So if the gas is bigger, we add, and if the air pressure is better, we subtract?
Yes.
Okay.
But then there will be weird ones like the last one.
Okay.
You want to try the second one?
Yeah.
Okay, try the second one.
If the air pressure is bigger.
I will tap dance for the people on the YouTube video. Did we get an answer?
Well,
Is my production system in your way? Is that in your way?
no, it's okay.
Kinda had to sketch this one first, right? Maybe not, I don't know, I always sketch stuff, I like pictures. So, gas to, and then it says, the mercury level is 30 meters higher and the side connects to the gas. Okay. So this, right here, this difference, but it's toward the gas. So do I add or subtract?
Subtract.
Subtract. And they told me that the air pressure was 101.3 kilopascals. And they didn't tell me what they want the pressure of the hydrogen in, so I get to do what I want. So I'm gonna change this. And it's easy to change this, right? Because 760 millimeters of mercury is equal to 101.3 kilopascals. So this is just 760. So 760 minus 30, because it pushed this way, so that means air pressure is greater than the tank pressure. So the gas pressure is that air pressure minus the difference. The difference in the two sides, that's the difference in their gases. If this were even, like if you came out of the tank and went to the air, or even if we just took it off the tank of gas, so there's air on this way and air on that way, they'd be even. But it isn't. So I'm gonna subtract this. And so it's gonna be 730. They're gonna give you three things, yeah.
So if it doesn't tell you like what to convert to, because like I did kilopascals, do we just assume
That's fine,
that
I know, I'll have both answers on the test.
you'll have both answers?
Yeah, so times 101.3 divided by 760, 97.3?
Yeah.
Yeah, I'll have both answers on the test
Okay.
as I'm grading them, you know what I mean?
Yeah.
So there's three things. There's the height of the mercury, there's the gas pressure, and the air pressure. And so they have to give you two, and you've got to figure out one of them. So these two are both the gas pressure. They could ask for the air pressure, and you would do it the same way. You would just have to figure out if it's more than less than the gas pressure, and then either add or subtract. This one, you have to draw the manometer correctly and label it. So that means you've got to figure out how high the mercury is and in which arm. So if it's connected to a tank of oxygen that has a pressure of 1.04 and air pressure is 1, just think about what that's going to look like first. So here's your tank of oxygen. And here's your air pressure. Okay, so this is 1 atmosphere. And this is 1.04 atmospheres. So which way is the mercury going to go? To the right or to the left?
Right.
It's going to go this way. This is greater, right? So it's going to push it. And it's going to push it this way. But they want you to also figure out how much. How much? So you can change it both to, and it has to be in millimeters now, right? Because there's no distance. It's measured in whatever this is, atmospheres. So you have to change it to millimeters. So you can subtract first, or you can change them both to millimeters and then subtract. Doesn't matter. I'm going to subtract first. So 1.04 atmospheres minus 1 atmosphere. That's the difference in their pressures. That's the difference in their pressures. So the difference is 0.04 atmospheres, but I can't label that because it's not a distance. It's just really nice that millimeters of mercury is also a distance. That's why this works. So I change it to millimeters of mercury. 760 millimeters of mercury is equal to 1 atmosphere. Atmospheres cancel out. You take 0.04 times 760. You get 30.4 millimeters. So it's going to be higher on this side by 30.4 millimeters. So if there was one like that on the test, you would get credit for the math, but then you would also get credit for making sure that you drew it on the correct side. How do we feel about the manometer problems? Okay. Better. You can Google manometer problems, PDF. That's what I do, and I get 40 million worksheets from all the chemistry teachers in the country. Do we need to do Dalton's law of partial pressure? Where we have a tank of gas, and there's 3 different gases in there, and here's the total pressure, and these are 2 of the individual pressures. How much is the last pressure? Are we okay with that?
Yeah, it's just subtracting.
It's just subtracting. We okay with that?
Yeah.
What about Graham's law of effusion?
Yeah.
So like, the rate at which, oh, that should be on there too, on the equation sheet. I better write that down. The rate of 1 compared to the rate of 2.
Square root of the mass.
Molar mass of the bigger one. I always do the bigger one, you don't have to. So if it was like helium and argon, I would make helium 1 and argon 2. And you're really just usually looking for it on the test, you definitely are, just looking for the difference in their rates. Like which one is going to spread out or effuse faster. So I always make the bigger one the second one. And so molar mass, I just kind of did a weird abbreviation. It's not really a true abbreviation. Molar mass of argon is, I don't know, because I can't read that far. That's not one we use a lot. 39.95. I mean, technically that would be grams per mole, but it doesn't matter because it's going to cancel out 4. And it's just a comparison. So just don't forget to take the square root. That seems to be the biggest deal. Divide first, take the square root, 3.2. So what that means, I call this helium and this argon. So the helium will spread throughout this room 3.2 times faster than the argon, mostly because it's little. Okay? Am I okay with that one? Okay. Intermolecular forces, is that the bad thing?
Yes.
You need an electronegativity sheet, and if you don't have these kind of, they're on the chart, right? You need these shapes. So those are the 3 kinds of intermolecular forces. Intermolecular forces are what make solids solids and liquids liquids and gases gases. So if you have a really big molecule that's not even polar, it's going to have a lot of dispersion forces. They all have dispersion forces because by definition, dispersion forces are caused by electrons. So what happens is the electrons are moving all over the place really, really, really fast, and then what happens is sometimes a whole bunch of them will bunch up on one side. And so when they bunch up on one side, that temporarily becomes a negative side and a positive side. Well, then that affects another similar atom close to it, and then that negative side will be attracted to that positive side. And then that's just what causes the dispersion forces that pull them together. And it'll be stronger the more electrons there are. Like 1 electron in hydrogen, that's why hydrogen is almost always a gas. The force of attraction between the hydrogen molecules is super small. It's not polar, it doesn't have hydrogen bonds, which is kind of weird, but we'll talk about that in a minute. So the bigger the atom, the more electrons, the stronger the force of attraction, the better chance of it being a solid at room temperature instead of like all the gases. The gases have smaller forces holding them together, that's why they're gases at room temperature. So these are the 3 kinds. Dispersion, dipole has to do with polar molecules. So if you don't know what the polar molecules are, like you don't have it memorized, you're going to have to draw a Lewis structure, look at the shape, and then look at the electronegativity differences to decide if that is a polar molecule. Hydrogen bonds have to be polar molecules. You can't have hydrogen bonds without having a polar molecule. So when you look at the polar molecule, if it contains hydrogen, like water, then it also has hydrogen bonds. So I'm not going to do water, but let's do hydrogen. And the way that I have this on the test, it'll be, I don't know if I have you drawing Lewis structures. I don't think I do. I think you have to draw the Lewis structure to get to this point. I ask you which kind of intermolecular forces are there, and this is what this abbreviation is down here, that IMF on the review stuff. So hydrogen making a molecule, we've done this. Hydrogen only makes one bond. Hydrogen has one valence electron, so when they connect and share electrons, they just make one bond, and that's what a molecule would look like. If I wanted to draw it as circles, it would, I don't know, look something like that, and this would be a hydrogen and that would be a hydrogen. So it definitely has dispersion. Everything has dispersion. So you immediately write down that this has dispersion forces because it has electrons, only two. Then you've got to figure out if this is a polar molecule. It's not. Electronegativity is a rating system of how well an atom controls the electrons. Hydrogen is it's 2.1, but that doesn't matter because they're both the same. So they're going to equally share. And so there isn't going to be a positive side and a negative side. So there is no polar molecule here. And if there's no polar molecule, even though those are hydrogen, there is no hydrogen bond. So that's it. It just has dispersion. If we move on to, I think the one that was on the worksheet that I'm still grading was hydrogen sulfide. Well, I don't know what's going to happen here. This could be lots of stuff. So from the very beginning, 2 hydrogen valence electrons, and then sulfur is in group 16, so there's 6 more. So there's 8 altogether that cause the bonding, that cause the sharing of the electrons. Hydrogen only wants to have 1 bond to be like helium. All the other ones want to have 4 bonds so that they're like the noble gases. So then I have to remember which one goes in the middle, which one goes in the middle that everybody else attaches to. The sulfur, because there's only one of them. And then I attach them. So there's a hydrogen, and there's a hydrogen. Does it matter that I put them on the top and the right? No. Does it matter if I put them at the top and the bottom? Yes. Wherever I start to draw them, I either go clockwise or counterclockwise. This is not right. Not right. Not right. Okay, so I've got that, and see how many valence electrons are left. Well, 2, 4. A line is a bond. A bond is 2 electrons being shared, so I have 4 left. Hydrogen's done. Hydrogen doesn't need any more. Okay, so I just have to put the last 2 around the sulfur. This is bent. That's the shape of it. 4 pairs around the central atom. 2 of them are shared, 2 are not shared. This is a bent shape. Bent can be polar. It is with water. That's water, right? Water's polar, I just know that because I know that, but I can prove it. What's oxygen's electronegativity?
3.5.
And then hydrogen is 2.1. So that means that this bond right here, the oxygen is a higher number, and it's a higher number by 0.6, I think, because if I can do, no, it's not. It's 1.4. So 1.4 is huge. That's in that range of 0.4 to 1.7. This is Polarville. When the electronegativity difference is between 0.4 and 1.7, that's polar. That means that this bond right here, the oxygen is controlling, yeah.
Can I write that in the equation sheet?
Yeah. The bond, this bond, the oxygen's controlling these 2 electrons most of the time. And then hydrogen here, same deal, same bond. The oxygen is controlling the electrons most of the time. So there are 2 polar bonds where the oxygen is keeping all of the negatives on this side of the molecule. And then on this side, that means that there's not as many, so that's gotta be positive. This is, water is a polar molecule, so that means this has dispersion, and it has dipole-dipole. And because, now that it's polar, I have to decide, is this, yeah, it is. It's hydrogen bonding as well, because they're hydrogens. Which brings us back to this. This definitely has dispersion, definitely. The hydrogen sulfide. I have to decide if it's polar or not. It looks like this picture, but the thing that makes water a polar molecule is this imbalance in the bonds between the 2, and that comes from the electronegativity. So hydrogen is still going to have a 2.1. What's sulfur?
2.5.
That's only a difference of 0.4. So chances are pretty good, although it's right at the bottom of it, this is not polar. It's not polar. So because it's not polar, even though there's hydrogens, there's no hydrogen bond. That just has dispersion. On the back of that worksheet,